Good afternoon. My name is Jim Clarke. I'm pleased to be here. The last time I gave the last talk on the last day, I looked out into the audience and saw my wife Ann, who is also in the same business, and a couple of other people, so it's really great to see all of you. I know you've had 3 long days, and you seem very alert, and I really hope I don't do anything to change that. But in any event, I'm at Vanderbilt. I want to acknowledge my colleague, Kevin Brown. Some of you may know Kevin. He was at Savannah River for some time and helped develop the vitrification work that's going on there. He went to Vienna, IASA, and then came back to Vanderbilt for a PhD. And some of these slides are his work. He did some really excellent risk evaluations for near-surface disposal facilities, and I'm going to show you some of the things he came up with. So what do we mean by environmental performance assessment? I'm going to focus pretty much on the environmental side of this. Performance assessment has been mentioned before today. It may have been mentioned earlier. I'm going to talk about both near-surface disposal facilities and show you a little bit of some of the details from the Yucca Mountain project where we get into transport processes and things like that. And we are in a position where we rely on performance assessments with respect to decision making for waste management and environmental restoration as well. And I think the major challenge is we're forecasting the performance of an engineered system over time periods that exceed our experience by orders of magnitude. I mean, we're really driving way beyond our headlights, even for near-surface disposal facilities. The currently favored designs have only been, in practice for probably just a few decades. And we're forecasting doses to compare to compliance levels for times that go out hundreds to thousands to 10,000 to NRC is now thinking about 20,000, and for Yucca Mountain 1 million. I think I can guess how all of us feel about that, but unfortunately that's the challenge we face. And then I really want to spend some time on conceptual models, because the more I do this, the more I think that the time we put into the conceptual model really is important. And I know there's a fascination with numerical models that we can do on supercomputers and things like that, but before we rush into that, I'd really like to see us spend a little more time on conceptual models. I'm becoming a real believer in the value of that. And then talk a little bit about uncertainty, but I suspect you've probably had a fair amount of that already. This is a nice publication, the National Commission on Radiation Protection and Measurement, back around, I think might have been 2005, but Roger Seitz, who's now at Savannah River, Matt Kozak, who was with Monitor Scientific, now in Terra, Dave Coker, who was at Oak Ridge, put together this nice document on performance assessment. This is focusing on near-surface facilities. And you can see there's kind of a logic that we go through with some iterations and some decisions. And you saw one definition of performance assessment already. Here's another one that I like, that I think complements that well. It's an iterative process. It involves site-specific and prospective modeling evaluations of the post-closure time phase of a waste disposal system to determine whether reasonable assurance of compliance with regulatory performance objectives can be demonstrated. It identifies critical data, design, and model development needs for defensible and cost-effective decisions, and develops operating limits. And I've added the material that's in boldface. So this definition I like. The regulatory framework And what I have up here is, I think, pretty much focused on near-surface facilities. The Department of Energy has Order 435.1 with a Radioactive Waste Management Manual 435.1-1. These are the order, of course, isn't, but the manual is in the process of being revised. The Nuclear Regulatory Commission has licensing requirements for land disposal of radioactive waste, 10 CFR 61. So these are commercial licensed facilities. The Environmental Protection Agency has the Superfund program, CERCLA, and RCRA, and the National Environmental Policy Act, and all of these may come into play depending on the material. And then the Ronald Reagan Section 3116 for waste determinations for what you might be able to leave in a tank after other material had been removed comes into play too. So these are some of the major regulations. Now here's where I think it really gets interesting. The compliance period for RCRA, which regulates disposal of hazardous waste, it was 30 years of post-closure monitoring and maintenance. Now, I don't think any of these facilities have achieved 30 years of post-closure monitoring and maintenance, so it will be interesting to see what happens when they do. But I suspect, they may be monitoring and maintaining beyond that. I think that's a reasonable expectation. CERCLA, for near-surface disposal facilities and environmental cleanups, has 5-year reviews. Some facilities have been through at least 3 of these reviews. The mill tailing closures, the design criteria are a minimum of 200 to 100 years. Low-level waste disposal facilities licensed by the Nuclear Regulatory Commission, 10,000 years was recommended in the EIS, and that was looked at again in a document, New Reg 1573, that supported the 10,000 years, but now there's an interest in taking that to 20,000 years. And in fact, they have issued an advance notice of proposed rulemaking to do that, and I think it's probably, that was in May, so it's probably still out for comments. Now, the difference between 20,000 years and 10,000 years, I have a hard time dealing with, quite frankly. I kind of like 200, I think we might be able to reasonably predict what might happen. So my guiding philosophy is take your best shot, and if you can, don't do anything you can't undo. But, that may not be possible. Then the repository that was spoken about earlier, 1,000 years, and how that came about. What do we need to comply with? What are the dose limits? This is a nice slide that Marty Letourneau presented. A couple of years ago, the Department of Energy established a performance assessment community of practice, and Vanderbilt and CRESP participates in that as well. Marty, of course, leads the LFRUG, the Low-Level Waste Federal Review Group, and put together this nice slide on dose limits. And on the interim, of course, the NCRP came out with essentially doubling background, taking it to 620 milligrams a year, but I really think that's a little misleading because the increase came from medical diagnostics. I think CAT scans were a big part of that. And I think if you're in a situation where you're getting this diagnostic test, then maybe your background is much higher, but if you're not in that situation, it probably isn't. So I might have preferred a range, but this is the one we normally think of around 300, 320, 350 or so milligrams per year. They came out, I guess it was about a year ago, maybe 2 years ago, with I think it was 620. But it was because of medical diagnostics. But you can see down here, The EPA has 4 millirems a year in drinking water, 10 in air. They like 15 on a near surface disposal facility or for decommissioning or whatever. They break out the groundwater pathway when they do that analysis. The NRC and the DOE for low-level waste use 25, and then you get up into higher levels. So we're down at the low end, demonstrating compliance with very low doses over long periods of time. And one of the things I do want to mention is that sometimes performance assessment is talked about as if it were alone. You just do a performance assessment, but actually it's a piece of a three-component system. First, you have performance objectives, which are in the regulations. The DOE has them in 435, and the NRC has them in 10 CFR 61. They're not the same. There are some differences. There are some similarities. And they're looking at that as well. Then you do the performance assessment. But the piece that I think we really need to be working, given these low doses and long compliance times, is this piece over here, which I'm calling performance confirmation. And the DOE has something called PA maintenance, where they do many of the things in this step that I would include in performance confirmation. But basically, you've designed a system. You've demonstrated through mathematical modeling that you can achieve the dose limit over the compliance period, and then you build it. So what do you do after that? Well, what can you do to build confidence in the performance assessment that was done? And there are laboratory studies you can do. There's natural analog work. There may be different kinds of monitoring that we don't do yet, but maybe we should be thinking about. It will give us additional information that may suggest that we need to go back and revise this performance assessment. We might do performance assessments for a number of different things. EPA doesn't require a performance assessment. They have prescriptive regulations for the design, but if you're dealing with a mixed waste, then you're dealing with EPA and NRC, and a performance assessment will get done somewhere. And then there are all these other areas for tank closures, saltstone at Savannah River, the decommissioning at a reactor site. And then these invariably involve engineered materials performance as well, the grout waste form and fill or whatever. This is another one of Marty's slides. And then at Idaho, historical disposal practices. These are some of the facilities they had. And I guess this is going to, kick in a little bit. This might be what we used to do. And actually, I had a slide also from Idaho that had all the drums stacked up very neatly, put on top of each other. And I think they realized the workers got more of a dose doing that than they did if they just ran it out the truck. So, another consideration. Let's see, wrong tool. Back a few years ago, they actually took some stuff out of the subsurface disposal area at Idaho, and this might be pit 4, some of the stuff that they retrieved. Definitions. Model calibration, and I started out doing atmospheric and surface water modeling back in the 70s. And so we always had to calibrate a model, and you calibrate a model by going out and making some measurements and then making sure your model predicts what you measured. So you're changing your tuning model parameters so the predictions measure data. There seems to be a little bit of an ambiguity between verification and validation, so I'll just give you my thinking for what it's worth. I understand model verification to be making sure that your model is correct and error-free, going back into your codes and doing all that work. Model validation. Kind of difficult when the compliance period is hundreds to thousands of years. So, sometimes we say models have been validated. I don't know if we can validate models when we're going out this time. So maybe, to my way of thinking, the best approach is performance confirmation approaches to build confidence in the models and the overall performance assessment. So that's, again, kind of the way I think about it. Models can be, time independent, steady state, or dynamic, 1 or 2, 3 dimensions. They can be simple, and they can be complex. And here's one way of looking at it. It's a simple model, but it works for me. It takes us from here to there. That's where we want to go. And then I love this quote attributed to Albert Einstein: everything should be as simple as possible, but no simpler. And everyone seems to know this quote, and everyone does seem to attribute it to Albert Einstein, but I have a lot of people that I know don't know where the quote came from. So one of my lawyer friends at the University of Miami challenged me to find the quote. And you did this years ago. Well, last year I did what I do now. If I want to know anything, I go to Google. So I went to Google and I Googled Albert Einstein quotes, and I got 40 pages. And I found this attributed to a talk he gave in German to some professional group, and it was apparently loosely translated to this, which is fine. I think it's words to live by. I've got a few more of my favorite quotes. It's late in the day. You're all tired, so we'll look at some quotes. But, again, performance assessment, everything should be as simple as possible, but no simpler. They've become very complex, and probably because they need to be, but I kind of like to start out simple and go from there. Again, this is the process I showed you. We have objectives, compliance objectives. We do a performance assessment, which is a mathematical modeling exercise, along with some data collection and other supporting activities. And then I'd like to see us spend today, I think this process is pretty well developed. I think we should be spending maybe a little more time on this one and trying to build confidence in the performance assessment that we've done. This may be a little hard to see on the screen. I think it shows up okay in your book. Let's start down here. Let's suppose we're looking at a near surface waste disposal facility, and that's a potential source. We don't want it to be a potential source, but it is. And so I like to think of containment as keeping the bad stuff in and keeping the people out. So those are the two main objectives of a near surface or a deep geologic repository. And then we've got stuff going on above it. We've got an engineered system, the purpose of which is, again, to keep water from going into this, because that turns out to be a major migration cause, taking it down to the subsurface and potentially to groundwater. We might have gases that could get out, so we need to deal with that, maybe radon at a mill tailing site or whatever. We've got these environmental pieces, the vadose zone, the saturated zone, surface water, the atmosphere, and then this is our soil and our engineered cover. And we've got all these different transport pathways and exposure scenarios down at a critical group, or the EPA calls it the reasonably maximally exposed individual. And then we want to know the risk of all of this. Or we want to demonstrate performance, but I really look at these as very common. They're very similar exercises. The performance assessment goes beyond a traditional risk assessment. But this is the way I would like to depict it. So Conceptual model and scenario issues, we'll get into this in a minute, but especially for a near surface disposal facility, we want to know how the cover is going to perform. We want to know how it might degrade over time and how the hydraulic conductivity of that system might increase, and therefore the infiltration of precipitation might increase as well. We have to worry about erosion and biointrusion. You've heard a lot about waste forms. That's an issue. We need to be concerned about preferred pathways and fracture development in the waste form, radionuclide release processes, different scenarios. Then once we get into the subsurface, fluid flow and radionuclide transport, fracture flow, equivalent. These are just different ways of modeling this. Radionuclide attenuation, absorption, matrix diffusion, chemical reaction, water chemistry. So these are some of the things we need to look at. Now this is a slide from the Yucca Mountain project. Major steps in a performance assessment. This was designed for Yucca Mountain, but I really think it's a good slide for any performance assessment. As John said, we need to develop and screen potential scenarios, and there were 3 climate scenarios for Yucca Mountain. These are shown up here. And we need to develop models and abstractions for the different environmental media and different performance factors. So we've got unsaturated zone flow. For Yucca Mountain, we had waste package, corrosion, waste form degradation, then subsurface flow, and then the biosphere, and also disruptive events. And we have to look at parameter ranges and uncertainties, and then construct the integrated total system performance assessment is the term that was used for Yucca Mountain, and do the calculations and then evaluate performance. So these are just a good slide, I think, that shows all the different steps for the performance assessment. Now, another one of my favorite quotes, and the first time I heard this, I thought it came from Yogi Berra because it really sounded like something yogi would say. Prediction is very difficult, especially if it's about the future. It's got to be, Yogi came after war, so that would have been difficult. But he was as you know, he was a theoretical physicist who had a model of the atom. And another one of my favorites, George Box, statistician, eminent statistician in Wisconsin. All models are wrong, but some are useful. A little cynical, maybe, but I think it has a lot of truth to it. We do our best to capture all the events and processes and features that are important and take our best shot. Now, I do want to spend some time on conceptual models because I think this might be a good opportunity to talk about something that may not get covered that much in other things that you've seen. Actually, the EPA issued the first guidance on conceptual models with the Superfund program, but the American Society for Testing of Materials, I think this was 2005, maybe somewhere around there, they defined a conceptual site model as a written or pictorial representation of an environmental system and the biological, physical, and chemical processes that determine contaminant transport from sources through the media to environmental receptors within the system. That was their definition. In another report, an NRC report, where NRC now is the National Academy, 2001, National Resource Council. They define a conceptual model, and this is, I think, consistent with the definition you saw earlier on performance assessment. They define a conceptual model as an evolving hypothesis, and I probably should have put that in bold too, but an evolving hypothesis identifying the important features, events, and processes, controlling fluid flow and contaminant transport, which was the subject of this manuscript, this book, actually, this report, Conceptual Models of Flow and Transport in the Fractured Beta Center. And they go on to say that it's an hypothesis because it must be tested for internal consistency and for its ability to represent the real system in a meaningful way. The hypothesis evolves, is revised and refined during testing and as new information is gathered. So sometimes we might not just have a conceptual model, we might have alternative conceptual models, and then we have to deal with that. We have to deal with the uncertainty that causes us to have more than one conceptual model. The definition I like is up here. It's very simple. It's just one sentence, but I think it has all the important pieces. Conceptual site models link sources of contamination to receptors, both human and ecological, through environmental transport pathways and exposure routes. So those, I think, are the four pieces of a conceptual model, and you just go from left to right. You have a source that goes through environmental transport and exposure routes to a receptor. I think they're very powerful tools, and they're used, a good conceptual model can be used to answer not just one question, but maybe several. They're powerful tools for site characterization, and that was really what the ASTM was looking at when they published their guidance on conceptual model. They're important to risk assessment because they provide the linkage from the source to the receptor. And they can also be used to evaluate different remedial technologies. So now I'm talking about legacy waste management, where we have waste that was put in a system that may not be environmentally protective, and now we have to fix it. So the ways of fixing it can be evaluated through this conceptual site model as well. They're depicted in different ways using flowcharts and environmental cross-sections or cartoons. So I'm going to show you some of both. So again, this is the way I like to think about a conceptual model. It links a source to a receptor, either human or ecological, through environmental transport pathways and exposure routes. So the environmental transport pathways would be the air pathway, vadose, groundwater, surface water. There might be some other food chain, maybe other transport processes there as well. The exposure routes might be external for radiation, inhalation, ingestion, dermal, and then the receptors can be either human or ecological. And of course, the source up here is what we're trying to evaluate. Trying to evaluate the performance of some engineered approach that would keep the bad stuff in and keep the people out. So this is a conceptual model, if you will, for the exposure part of that. And this actually came from the Yucca Mountain Project as well. One of the disruptive scenarios was magma intrusion and volcanic ash. This would be the critical group down at the Amargosa Valley. Then the inhalation pathway, the ingestion pathway, the external pathway, and then all the different ways people could be exposed to radionuclides being transported from the repository. So this is a nice little cartoon that I think shows a piece of the conceptual model. And that's really all the cartoons can do, I think, is just show pieces of the conceptual model. They get pretty unwieldy if you try to do more. This is the hydrologic cycle, basic to everything, with water coming in and going back up and becoming a source of flow and transport for materials that are either near the surface or maybe even in a deep repository. So this is kind of like a driving force that we have to deal with when we look at migration. Here's another conceptual model. This is a Superfund site in New Jersey, the Ciba-Geigy Corporation. They manufactured organic chemicals and dyes. And over here they had a number of chemical processing buildings which became sources through leaks and pipeline drains and things like that. They had several disposal areas. They had lagoons, they had a wastewater treatment system, they had a drum landfill. This is going back into the in the 80s. It's a kind of a sandy, silty Atlantic coastal environment where you have the Toms River. Right, by the way, it's a very pretty area. It's right, it's very near the coast. And this is the geology. And the concern was if stuff comes out of the buildings or the lagoons or the old wastewater treatment system, is there a pathway that would take it to a residential community that was over here? So you had to look at local transport and then regional transport, and there are different aquifers. And you can see that anything coming from here would most likely discharge to the river unless it were coming, from far away. So one of the early arguments was that the Toms River is an effective barrier. Actually, it turned out it wasn't, because they had their wastewater treatment system had a pipeline that went out to an ocean outfall, and that broke, and that changed everything. But this is, I think, a good example of a water transport conceptual model in a silty, sandy geology. And then here's really what we're dealing with. We've got for near-surface disposal, we've got an engineered facility that we put waste in, and that waste is in some waste form. It may be grouted and inside a drum. We don't put liquids in near-surface disposal anymore, so there's some kind of waste form here. And then one of the problems is, and one of the confounders to these long compliance times, is we have to deal with all these natural processes. And I like to think of it in terms of the second law of thermodynamics, which is kind of like, nature doesn't like you putting something in one place and leaving it there. But you have to deal with population encroachment, perhaps. A good example is the Rocky Flats site in Denver. You've got radiation that, depending on your cover here, can be a factor. You've got surface water, plant intrusion, animal intrusion, freeze-thaw processes near the surface, degradation, and then, here's your waste form, different waste forms. And then, of course, what you don't want to happen is that the system degrades, stuff gets out of it, water gets in, water transports material through the vadose zone down to the aquifer, and then there's potential exposure to humans and ecology. And of course, you can have erosion and other things that could transport material to surface water too. And then you've always got atmospheric transport if these systems in here break down and you're dealing with gases. So here's another cartoon that now shows the system, but now shows some ecology around it as well. The EPA approach is to use a cover, a RCRA subtitle C, this would be for hazardous waste, that is called a resistive barrier, because the purpose of this cover is to keep water out. So the technology evolved to what is called a composite barrier, where you have a compacted clay layer with very low hydraulic conductivity, and then above that you have a geomembrane or a plastic liner as well. So you've kind of got a little bit of defense and depth. If your plastic liner is damaged through construction or whatever, then you've got the clay, and of course if the clay desiccates, some of the early systems just used the clay, and they found out that when the clay dried out, there were preferred pathways through it, so geomembranes were put above it. And then, if you're dealing with gases, you might have to collect them. If you're worried about biointrusion, you might put a barrier in here. There's a drainage layer, the intent of which is to keep the water off the composite barrier. So this is an engineered system that is a prescriptive requirement under RCRA for hazardous waste, and maybe for mixed waste, but the regulations do have a way where if you can demonstrate that an alternative approach is equally protective, then you may be able to negotiate that. And this is, putting it in, there's they're putting the clay and then the plastic over it. These systems, if they fail, probably are going to fail pretty quickly, because one of the biggest issues, of course, is the quality control and putting the system in, and putting the plastic over a rock, or doing something that it's going to deteriorate the protection that this was provide. If they're put in well, they're probably going to last for a while. How long? I don't think we know. And then this is trying to put in some other features as well, where now you've got all your engineered systems, and you also have institutional controls as well. So the environmental setting, the engineered barriers, the monitoring techniques, and then all the different things to, again, mainly to try to keep the people out as well. Event trees were mentioned. I had a student who's came back again for a PhD, and he's now at Savannah River, Kevin Kostelnik. He was at Idaho. Put together a series of event trees to look at different types of errors that could lead to problems with institutional control breakdown. So here he's got at the top an information management error, and then down here different initiating events. And you can work up the event tree to, through and or gates, and see what combination could lead to a breakdown. I think these are very useful in evaluating scenarios that you would then use in the performance assessment with a conceptual model. Here's another way of illustrating a conceptual model. We've got the source, the environmental media, different parts of the environment. So these are the primary contaminant releases, the media, secondary media, exposure pathways, and then the receptors over here. So again, we're linking the receptors to the source through exposure routes and environmental transport pathways. This is the subsurface disposal area at Idaho that Kevin worked on. One of his case studies, the other concerned the near-surface disposal facilities, the so-called SWASs at Oak Ridge. But here's the subsurface disposal area, about 97 acres, mainly transuranic waste that came from Rocky Flats. A lot of it came from Rocky Flats. And different pits and trenches. You can see a legend over here. Kevin put this together for a conceptual barrier site model, where now you're looking at the source, the environmental transport pathways, you're looking at some of the events that could cause releases. And, it turned out to be a very, very useful way of depicting what could happen. Then the conceptual model can also be used to evaluate remedial alternatives. So what you want to do is right now, there's a linkage from the source to a receptor. You want to disrupt that linkage either by removing it or by blocking it in some way. So you can show what different remedial actions might do to stop contaminants from going from the source to the receptors. And then you can improve that as well by backing it up a little bit and looking at some events, and then the transport, the exposure pathways, and all of that. So, again, I like to think of a conceptual site model as it links the sources to the receptors through environmental transport pathways and exposure routes. And I have one more quote for you, but I have to give it a proper introduction. Are any of you jazz music fans? Any of you like jazz? Some of this is probably going to be before your time, but any of you heard of Elvin Jones? Elvin, and he is. Tell me about Elvin. What do you know about Elvin?
No, just I know the name from my dad.
Okay, he was
I used to play a vinyl.
Yeah, he played with John Coltrane, and he played with, and he was a very innovative drummer. In a former life, I played drums. I was a professional musician through college, and still do it in Nashville whenever I can get somebody to call me up. And do play with a little band, but I'm not professional anymore because they stopped paying me. But that's okay. I have a day job. So, but Elvin Jones was a very innovative drummer, and he was playing around the time. If you turn on the radio, if you like popular music, chances are you're going to hear something in what's called 4/4. 4 bars to a measure, and you just count it 1, 2, 3, 4, and then you go back to 1. Well, with Dave Brubeck in a song called Take 5, which is 5/4, and some other things that are going and some of the alternative music today is in all kinds of different time signatures, but 5/4 you went to 5, 1, 2, 3, 4, 5, and then back to 1, and 7/4 you go all the way to 7 and go back to 1. And here's Elvin's quote, which I think sums up my feeling about the importance of a site conceptual model very well. He says, if you can't find the 1, forget it. So if you can't get back to the 1, you're going to throw the whole band off, and everything's going to go to hell. Okay, well, if your conceptual model is wrong, all the numerical modeling in the world may not get you where you need to go. So I like this quote because I like Elvin, I like drums, but can't find the 1, you're in trouble. Another type of cover, I showed you a resistive cover. This is gaining popularity in the West, where there's a very good chance it might perform well, and that's rather than try to put some engineered thing in here that can break down. This is called an evapotranspiration cover, or Craig Benson calls it a water balance cover. There are different names for it. But what you do is you use evapotranspiration as a way of taking water out